Okay, welcome back. Happy Wednesday. Today, our 18th class. Today we are back in chapter 1, which means we are reviewing a pre-calculus topic. Today we are reviewing trigonometric functions. Next class is our project check-in day. As usual, the closer you are to being on my recommended schedule, the more you will get out of that period next class. This is coming Friday. I'm also going to hand out a take-home quiz on Friday, and you'll have the weekend to take care of that. And then coming back on Monday, we will do derivatives of trig functions. So reviewing trig functions today for the purposes of doing calculus on Monday with the trig functions. There's also going to be another quiz assigned there on Monday. Questions on that one is, yeah, it is take home, but it's one where you have many attempts at it and I give you the answers ahead of time. It's the friendliest quiz you could possibly hope for. We'll talk about it. Any questions on the calendar? Okay, so let's start in on page 31, and I will warn you that you guys all took a pre-calculus class, and I'll estimate that roughly half of that pre-calculus class was based on trigonometry, maybe a little bit less, but a good percentage of that pre-calc class was based on trig. You spent half of a semester doing trig. Today, we have an hour and 10 minutes. It's going to be fairly intense, but it's supposed to be a review. Hopefully it's not overwhelming, but we are shoving a lot of review of trig into our 1 period review day today. Okay, how do we convert between degrees and radians? Well, there is an identity that we know. A certain number of degrees equals a certain number of radians. Let's put the magic numbers in. 180 degrees is equal to pi radians. And the way that we use those facts is that, for example, 180 degrees divided by pi radians has the value of 1, right? Because they are exactly the same as each other. Numerator and denominator equal each other, so that fraction equals 1. So you could take, for example, a radian angle like, I don't know, 3 pi over 4, and multiply it by this fancy form of 1, and you get the corresponding degree angle, okay? And if you wanted to go the other direction, you multiply by the reciprocal of this thing. You will get to do that in the activities. In calculus, we assume radian mode unless noted otherwise. There is a very good reason for doing this, which will become clear during Monday's class when we do the derivatives of the trig functions. But take my word for it, radians are much better for calculus than degrees, which means if you are coming from physics right before this class into this class, and in physics your calculator is in degree mode, when you walk in that door, you change your calculator to radian mode, right? We are in radians here in this class all semester. Okay, number 2. Some facts about functions of this form, a times sine of bx plus c plus d, and then the same thing with cosine. These are both called sinusoidal functions, really useful for modeling any phenomena which repeats, like sines and cosine functions, right? The amplitude, that is how high and how low the repeating function gets from the middle. How far from the middle is a, although technically it's the absolute value of a. If a were -3, for example, then I would say the amplitude is +3. Okay, if you wanted to think about how much the trig function has been shifted from its like normal, like just plain sine of x graph or just plain cosine of x graph, the horizontal shift is c. That plus c there. Notice that the x plus c is in parentheses and we've factored out the b. That's going to be important for us to have it in that form. The vertical shift, this is plus d. That's the midline. That's that's where the x-axis moves to. And then finally, if you want to get the period, that is how long it takes for the thing to repeat horizontally, you have to do a little calculation based on what you see here. The period is related to b, but the period is not b. The period is 2 pi divided by b. Okay? We will use those facts in the activity. All right, that was 2 weeks of trig. Moving on. One important key to success is familiarity with the unit circle. Let's fill in, since all the blanks in the top half, we'll just fill in a few. I don't know what happened over here, but I do know what happened. There's a text box floating on top of this picture, and somehow the two of them ended up disconnected from each other. So I will say that these things that appear to be floating were supposed to go in these blanks. So go ahead and put them in these blanks. Pi over 6 and root 3 over 2 and 1 over 2. Somehow they just got moved a little bit. Okay, so let's fill in, I don't know, let's do 4 more of these lines here, exactly all that information. So the next important angle up from 30 degrees is 45 degrees. But in this class, we don't speak in degrees, we speak in radians. Does anybody know the corresponding radian for 45 degrees? However, 4 is good. And then we need some numbers, and the numbers that go in here are equal to each other, but neither of them is these numbers here. What are they? Square root of 2 over 2 for both of them. And it makes sense they're equal, right? Because this thing is like smack dab in the middle of that first quadrant. Okay, let's fill in the next line up. 30 degrees, 45 degrees. Next is 60 degrees. That's pi over 3. Yeah, these numbers are the same as the 30-degree numbers, but the x and y are reversed, right? Symmetry here. So this is a 1/2 and a root 3 over 2. Okay, let's do the one up at the top. How many degrees? That's 90. How many radians? Pi over 2 is good. And then there are numbers up here. I mean, this is a point. What's the x? It is 0. What's the y? It's a 1. This is the unit circle, so named because the radius is 1. So that's why it's a 1 going up there. And then we'll do one more and call it a day. So last one over here. Let's see. So it's 60, 90. What's next here? That's a 120. And then I start to, like, I've got all that stuff memorized in the first quadrant, but then I have to really start thinking. I have to, like, calculate once I get outside of that first quadrant. But at some point, somebody told me that there is a pattern here in these pi numbers, pi over 6, pi over 4, pi over 3, pi over 2, which does not look like any kind of pattern that I'm familiar with. But he told me that there's a hidden pattern here, and everything has to do with pi over 12. So let's count. Turns out that pi over 12 is 15 degrees right here. Pi over 12 is 15 degrees. All of these things are multiples of 15 degrees. It's just that we skip some of them, right? We don't actually care about 15 degrees, and we don't care about 75, and we don't care about 105. But if we pay attention to those things, just temporarily, the pattern will become apparent. So I will write it here. If you dig this one, you can remember it too. So that is pi over 15, the one that we skip. The next one must be 2 pi, sorry, not pi over 15, pi over 12. Pi over 12. 15 degrees. That one's pi over 12. The next one is just double that, right? 2 pi over 12. The next one is 3 pi over 12. After that, 4 pi over 12. There's one that we skip, but I'll write it. 5 pi over 12. Up at the top, 6 pi over 12. The next one that we skip, 7 pi over 12. And the one we're working on here, 7 pi. I jumped to the 8. 7 pi over 12. And then 8 pi over 12. Okay, that's the pattern that I can understand perfectly well. And if we reduce them, we get familiar numbers. 2 pi over 12 reduces to pi over 6. 3 pi over 12 reduces to pi over 4. 4 pi over 12 is pi over 3. We skip the 5 pi over 6. 6 pi over 12 is pi over 2. We skip the 7. What is 8 pi over 12? That is 2 pi over 3, which is that radian angle right there. So I like that pattern. If you like it, you can use it. Okay, and then the numbers in the parentheses, that is the x and y coordinates. They're copies of something over there, except some might be negative. So I guess that's the same as the orange one. The old x used to be positive 1/2. What's the new x? Negative 1/2. So that goes right there. We'll even make it orange. Negative 1/2 there. And then the y used to be root 3 over 2. It's still root 3 over 2. All right, and so you can fill the rest of it in later. It's probably a good exercise to fill that in on your own. The fact is you'll be able to use a copy of this like already filled in on any quiz or test, and you'll find a filled in copy at the start of the activities today. Okay, moving on. On the unit circle, we define all 6 of our trig functions. The sine of t is defined to be the y coordinate of the point. Every one of those points has a y coordinate. The sine of the angle is the y coordinate. So for example, the sine of, we just did 2 pi over 3. What was the y coordinate at that point? What's the y coordinate of the last point we wrote? Was root 3 over 2, so that means that the sine of that angle, 2 pi over 3, is the y coordinate. It is root 3 over 2, okay? So every one of those points gives you a sine value, that's the y, and it also gives you a cosine value, that's the x, and it also gives you a tangent value, that is y divided by x. So those are the three trig functions that get the most love and attention. The 3 neglected trig functions are firmly related to those 3. They are just the reciprocals. So cosecant is related to sine. It is the reciprocal. Secant is related to cosine. And then cotan is related to tan, x over y. Okay, on the next page, that was like another 2 weeks right there. All right, on the next page, in a right triangle, you had this ridiculous acronym that you memorized and was only useful if you could spell it. It's a problem if you can't spell it, but it tells you how we define the 3 favorite trig functions for a right triangle. Sine is opposite over hypotenuse, so we'll just abbreviate there, opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then tangent, opposite over adjacent. You could fill in these 3. They're just the reciprocals of those 3, but let's continue to neglect those 3. Moving on. Basic trig things that you should memorize. We've got a few quotient identities. So we already knew that tangent was opposite over adjacent, and we also saw on the previous page tangent was y over x. But another way to think about tan, relating it to sine and cosine, is that tan turns out to be sine over cosine. Cotangent, of course, is the reciprocal, so cosine over sine makes sense there. And then we've already seen these other 2. These are just the plain reciprocal identities, that cosecant is 1 over sine and secant is 1 over cosine. All right, Pythagorean identities. There are 3 of them. You can build the other 2 based on the first one. So the main one is sine squared plus cosine squared is 1. As long as you put the same angle inside of both of those functions, you will get 1, no matter what angle you pick. I will just remind you that sine squared of t literally means sine of t. Calculate that thing and then square the answer. Us putting the squared there is our way of saving the 2 parentheses. Mathematicians are incredibly efficient, and that's the only reason we have that notation, but it means that you as math students need to be familiar with the notation, right? So you save 2 parentheses, but you got to make sure you know what you're doing. Okay, you can get the other 2 identities by dividing by the right thing. So for example, if I divide everything by sine squared, if I divide everything in this equation by sine squared here divided by the sine squared is 1, plus cosine squared divided by sine squared. That's one of our other trig functions, look. Yeah, it's related to cotan, right? Cosine over sine is cotan, but I said cosine squared over sine squared, so that is cotan squared. See? Equals, and then again, we were dividing everything by sine squared, and 1 over sine squared is cosecant squared. So that's one of the other Pythagorean identities. You can get the last one by dividing all 3 of these things by cosine squared. And so we'll just write it, it's tan squared plus 1 equals secant squared. Okay, so lots of identities, lots of facts, lots of theorems. Ultimately, at the end of the day, we want to be able to solve some problems using trigonometry. So here's our first one. Rabbit population varies sinusoidally between 3,000 and 5,000 rabbits. The last 2 times the population reached 5,000 rabbits were in 1990 and 2000. So what we're going to do is model the population of rabbits as a function of t, which will be the number of years since 2000. So we're looking for an equation. And then we will use our equation to figure out when the rabbit population will reach 4,500. Okay, so that's the ultimate goal. All right, for me, I have to have a picture for all of these kinds of problems. So let's go ahead and draw a picture here. So we're letting t equal the number of years since 2000. So that means that my 2000 spot, I mean, it's t equals 0, but it's really representing the year 2000. So the other data point that I have is 1990. Where do I put that? That's -10. So we'll put that over here. -10 there. And it says that the population was at 5,000 at both of these times. So I'm putting 5,000 up here, and I'm putting 2 dots. It was 5,000 in 1990, and again in the year 2000. Okay, we also need to use the 3,000. The 3,000 is the bottom, so we're going to put the 3,000 at the bottom. I will exaggerate it, and it's out of scale here. But we should know when it hit 3,000 in the middle, right? If it's going to be a sine or cosine function, it's got all of this symmetry. And so 3,000 was right there in the middle, so that is at -5. And we will put our dot right there. All right, so we've got our 3 dots. That's enough for us to see the pattern. You can go ahead and draw one full period of this thing here. And then, I don't know, draw like another period out there and another one back here, whatever you want. But I mean, it goes forever, both directions. And our task is to find the equation of that curve right there. Okay, so we got 2 choices. We can either view this thing right here as a sine function or as a cosine function. Neither of them is wrong. We just have to make sure that we can find the right pieces. So let's fill in A and B and was it just C and D? What are the other letters we had? Okay. So these are some of the letters from the very beginning of this demo. Okay, let's go ahead and start with the D. The D was the midline. What is the middle? 4,000. And it's positive because this thing is above the x-axis. Okay, we're going to come back to C. Let's move on to A. A is the amplitude. It's how far from the middle to get to the top or the bottom. We've already figured out the middle is 4,000, so it's either 1,000 up or 1,000 down. Either way, it's 1,000. Okay. B is related to the period. So first we're going to write down what the period is. This is like a side calculation here. So the period, just by looking, is how long it takes to do one complete cycle. 10 years. So the period is 10. And the way that we calculate the B based on the period is 2 pi divided by the period. This is an equivalent version of the equation we wrote on the first page. So 2 pi over 10, which will reduce to pi over 5. That is B. Any questions on any of those? Okay, the C value I've left last, and we did that on purpose. The C represents the horizontal shift from the normal sine or cosine. Well, how much you shift depends on which function you pick. So we're going to pick the easy one first, and then we'll pick the harder one second. The easy one is to think about like what the graphs of sine and cosine look like normally. So that right there is like a normal cosine graph. And then this is a normal sine graph. And if I think of them starting on the y-axis, now the start is not a good word because it goes forever both directions. But if I think of the start as being the y-axis, then I would say that the sine starts in the middle and goes up. And cosine starts at the top and goes down. Which one is this green thing? That is a cosine. Starts at the top and goes down. So if I choose to view it as a cosine, then how much do I need to horizontally shift? Not at all. Zero as a cosine. But sometimes you don't have the ability to just make it be a sine or a cosine. It could be that it starts someplace in between, not the top, not the middle, not the bottom. So I do need us to be able to shift it because we might have to in some cases. So let's think about the graph of sine normally starts in the middle. And the question is, how do we take that graph, which normally starts in the middle, and move it so that it becomes this graph right here? So what we are after is the quote starting point. We need to find this guy right here. We need to find a point on our green thing where it's in the middle going up. There's lots of them. For example, here, in the middle going up. Just as well could have picked over here. Could I pick this one? No, that's in the middle going down. That's not one of our winners, but we could have picked this guy over here. So you pick any of them. I will pick, maybe blue is not the best color there. We'll pick this guy in black. So just thinking about the symmetry of the sine or cosine function, what is the x value or t value there? Negative 2.5. It's smack dab in the middle of the low and the high. So negative 2.5. What that means is that we took our original sine graph and we shifted it left 2.5. Yeah? Okay, so we just have to shift it left 2.5. So let's write this here. Or I'm going to put 2.5. I don't know if it's positive or negative. We'll analyze. But if I'm thinking of a sine graph, it is 2.5. Okay, going back to the previous page, like the very top of the previous page, it was inside of parentheses x plus c. So the question is, if you want to shift left, should it be x plus 2.5 or should it be x minus 2.5? I heard minus. I heard plus. I heard both. It goes the opposite of what you might expect it to do. So if you are shifting left, even though that feels like a negative, it's actually plus. Anything inside of the function is opposite what you might expect. So we'll put a plus there. Okay, so that means that we can write two different equations here. All of the work is done. So that means that that green thing, I'll even write it here in green, y equals, okay, so our formula was a times the cosine, so 1,000 cosine of, then we put the b, pi over 5, parentheses, x, and then we decided to go left. We do need to add 2.5, and then plus the, I'm sorry, that's not right. Cosine, we decided that we didn't need to shift it at all. So it was just plus nothing. And then at the end, plus d, plus 4,000. Or we could do the same exact thing, but sine. And we've decided that what do we need to put in here? Plus 2.5. That will take the thing and shift it left 2.5. And that's exactly what we need to do. Take the original sine, shift it left to make it land on that. Okay, so one thing I like to do, and I've loaned out a couple of graphing calculators. I think a bunch of us have graphing calculators, so this will be one of our rare graphing calculators day. But I really like to just check myself and type in the function. So 1,000, you don't need to do this now on yours. You'll be able to do it during the activity. Pi divided by 5 times x plus 4,000. All right, now we're going to pick our window. If we just graph this thing, we see absolutely nothing because this thing is up there between 3,000 and 5,000. So don't bother graphing it without thinking about the window. So I'm going to go into my window. If I want like one single period of this thing, like I want a tight graph of a single period, what is my minimum x? Negative 10. What is my maximum x? 0. I'm really making this a tight fit to see if I got it right. What is my minimum y? 3,000. And my maximum y? 5,000, I don't know, we'll go by 500s or something. Okay, if I did this right, we should see exactly one period, and it should start at the top left pixel of my window and go to the bottom middle pixel and end up at the top right. So let's give it a shot. One other thing, anytime we hit sine or cosine in this class, what mode? Radian. I didn't check, and this is wrong. And in fact, the result is something that is not what I expected. I expected to see one complete period of this thing. Instead, I get that, which doesn't look like sine or cosine at all. It's an indication that something is fishy. We chose radians when we did this 2 pi over b. We didn't do any calculus in this problem, but we chose radians right there. Okay, top left pixel to bottom middle pixel to top right pixel. How satisfying is that? Come on, that is fantastic. Like you think about like, maybe I just have control issues, but I'm just like, I totally own that function right there, right? Like found it exactly, like it tried to hide from me. So I know exactly where you are. Okay, the other thing that I like to do is check my other function. So let's go ahead and check the other one. So it's the same 1,000. It's the same, in fact, I'll do them both at the same time. How about that? 1,000 sine of, so here we're doing extra, so what are we doing? Pi over 5 and then extra parentheses, x plus 2.5. Oh, pi over, thank you. Pi over 5, x plus 2.5, close, close, plus 4,000. Now, if I did this right, what am I going to see when I hit the graph button? I'm not going to see anything because it's supposed to land exactly on the thing that's already there. So I don't know if you've seen this before, but if you go all the way left, it doesn't appear that you can maybe go over there, but you can go all the way left and hit enter and you get a few different options. And that first one is the one that I want. That's going to draw more thickly. So it should draw right on top. The other one thicker. Good? Okay. All right, so then the question is, when will the population hit exactly 4,500? So it says we're going to do this one 2 ways, one algebraically and one with a graphing utility. Let's do the algebraic way first. Okay, algebraic way. That 4,500, is that the x or is that the y? That's the y. So we're going to rewrite that entire equation with a 4,500. Now, if I were doing this problem like personally, I would pick the first equation because that's the simpler one. But sometimes you have to deal with the more complicated equation here. So let's go ahead and use the second one because it's more complicated. So we're going to put 4,500 for the y and copy everything else. Okay, so some basic algebra before we get to the basic trig. What do I need to move first? Trying to get x by itself. There's a lot of numbers that need to go to the other side. The 4,000 needs to go first, so we will subtract 4,000. So we get 500 equals all of this. Which number goes next? 1,000 goes next. So 500 over 1,000 equals sine of this stuff. And then we'll just reduce that to half. Okay, so now we get to the trig part of this equation solving. What is the opposite of taking the sine of something? Is the inverse sine or the arc sine. So what we do is take the inverse sine of both sides of this equation. So the left-hand side becomes inverse sine of a half. The right-hand side, just imagining because I'm not going to write it, inverse sine in front of the right-hand side cancels with the sign that's already there, and we just get what's inside. Pi over 5, x plus 2.5. Okay, inverse sine of a half happens to be one of the few nice angles that we know stuff about. Like if you just go to the unit circle, go to your unit circle, and we're looking for a place where the sine is equal to a half, which means the y coordinate is equal to a half because sine is the y coordinate, cosine was the x. So find me an angle in that first quadrant where the y coordinate is a half. Which one? Is it 60 or is it 30? The y coordinate is supposed to be a half, so we're at 30, yeah? And so you could say 30 degrees, but we are in radian mode the whole time, so we should be saying pi over 6. So this guy right here is pi over 6. But the fact is, in almost every real problem, the inverse sign is not going to give you a nice number. It's not going to be one of the few points that we pay attention to on the unit circle. So this is where we type on the calculator. And you can do this on the graphing calculator, but also just as well on the scientific calculator. And we're just doing inverse sine of half. And we get a decimal, which probably won't look at all familiar, but it is pi over 6. Like if I typed in pi over 6 on the calculator, it would give me that decimal, all right? But like I said, most of the time it's not anything nice like pi over 6. I'm going to do something kind of funny here. So this is disturbing to a lot of folks to see the calculator say that inverse sine of a half is 0.52 and change, and then in the very next heartbeat, inverse sine of a half is 30. Well, what did I change in between those two? Is the mode, right? Like we're like, yes, 30 degrees is the same as the 0.52 radians. They're equal to each other. So again, you got to make sure that before you hit any of these three buttons, or any of the three yellow buttons right above, that you are in the right mode, radian mode for us. Okay, so 0.52 is close enough for our purposes. We'll say this is right around 0.52. Okay, and now we're almost done. The rest of this is pretty easy. How do I move the pi over 5 to the other side? You could divide by pi over 5. A little bit shorter would be, I'm going to twist my elbow out of socket here. So multiply by the reciprocal, right? So multiply by 5 over pi. So 5 over pi on this side, and then 5 over pi cancels on this side. Okay, and then finally subtract the 2.5. So 5 over pi, 0.52 minus 2.5. And then we'll get a decimal here. Notice that I'm not going to retype the 0.52 because that would be introducing rounding, and I don't need to do that. We'll just have the full number that the calculator has in its memory right now, and I will just right now multiply by 5 divided by pi. And you can do this on your scientific calculator as well. It doesn't have to be a graphing one. Mine is 2.5. Okay, so negative 1.6 repeating. So I guess that's negative, what, 5/3? Again, normally this would not be a nice number. It just happens to be a nice number because of the half that we ended up with. Okay, so what does that mean? Well, let's take a look at our picture. Negative 1.6 repeating. Taking a look at our graph. All right, taking a look at our graph. We were looking for a place where the population was how much? 4,500. So that's pretty close to the top, not quite at the top. I'll put it, I don't know, right around there. 4,500. And there are lots of places where the graph is equal to 4,500 as a y. We could go there, we could go way out here, we could go here, we could go here, and we can go further back in time. What did we just find? That negative 1.66 was that's this guy right here. That's what we found. Right? We found the first time before 0 where this thing was up at 4,500 as a population. So again, you can see I'm not to scale here. I guess maybe 4,500 should have been a little bit higher, but the number at least is feasible, something between 0 and -5. Okay, that was just one answer, but there's lots of them. Think about symmetry. What's the next positive one? It was positive 1.6 repeating, right? So that's easy. But it's the other ones that are maybe a little bit tougher to think about, and we do need to be able to find other ones like that. Let me remind you that the next top is at what time? 10. And so how about this orange one right here? It's 10 minus the 1.66. That 1.66 is just telling you how far from the top. Doesn't matter whether it's before or after. Just again, think about the symmetry. So this right here is 10 minus 1.6 and change. So 8.3, repeating, 2008 and change. Okay. So that's like 6 weeks of trig in 35 minutes.
How would you want us to rate that? Would it be -1 and 2/3, 5?
Yeah, you could write it that way. Probably for like any like actual like word problems, it's going to say to the nearest hundredth or thousandth, something like that. And then you would just write, 8.33 years. Yeah. All right. So I know that that demo was long. Like I said, 6 weeks of free calculus right there in 35 minutes. You know what else is long is the activity. So there's really no hope for you to finish it, but you're just going to hopefully review some stuff and it'll come back to you. All right. Don't get hung up. If you end up spending too much time on one section, call me over right away and let's see how far we can get.